heading toward a vast structure or even another universe. Within the Laniakea supercluster, galaxies appear to move toward an unexplained mass known as the Great Attractor. If similar anomalies exist on even larger cosmic scales, fast-traveling galaxies could be responding to these unseen forces. Conversely, instead of being drawn toward a mass concentration, they might be repelled by voids, massive underdense regions that create gravitational imbalances. Tracking their trajectories over millions of years could help astronomers identify these hidden structures. Another possibility is that some of these galaxies could be escaping the universe itself. If space is expanding at an accelerating rate, certain objects may reach the cosmic event horizon, a boundary beyond which they recede faster than the speed of light due to spacetime expansion. From our perspective, they would fade into infrared darkness, never to be seen again. If one of these high-velocity galaxies breaks free from the cosmic web, the large-scale structure of interconnected galaxies and dark matter filaments, it may enter a completely empty region of space where gravitational interactions are minimal. Some physicists speculate that if spacetime has hidden topologies, wormholes, or interdimensional pathways, such a galaxy could theoretically exit into another universe, making it unobservable forever. If astronomers detect a stellar system that appears to be vanishing without explanation, it could provide the first direct evidence of such an event. While most of these galaxies are thought to move away from major structures, some might eventually collide with others at extreme velocities. A high-speed impact between two galaxies traveling at thousands of kilometers per second would release unimaginable amounts of energy, possibly creating an entirely new class of high-energy astrophysical events. Such a hypercollision could trigger the most violent starbursts ever observed, compressing gas into dense clouds that rapidly form new stars. However, it could also lead to the destruction of galactic structures, tearing apart stellar systems and forming long tidal streams of stars and gas stretching across millions of light-years. If one of these fast-moving galaxies collides with a normal galaxy, it might even lead to the formation of an ultramassive black hole, disrupting the gravitational balance of its surroundings. Detecting such an event would provide valuable insights into the limits of cosmic energy transfer and the behavior of galaxies under extreme conditions. Another strange idea is that some of these galaxies might not be what they seem. Certain anomalies in their motion could indicate that they are faint relics from the early universe. If a galaxy formed soon after the Big Bang and was ejected at high speed, its light might only now be reaching us, making it appear as though it exists in a different cosmic epoch. Others proposed that some of these high-velocity galaxies could be composed mostly of dark matter, making them nearly invisible except for their gravitational effects. If such formations exist, they could be drifting through space largely undetected, interacting only through gravity. Even more speculative is the idea that some of these fast-traveling galaxies might be holographic projections or manifestations of unknown physics, possibly revealing dimensions or an emergent cosmic order. Future deep space surveys could help determine whether they are entirely normal or something far strange. If an civilization one of these high-velocity its experience is radically different from our own. Due to relativistic time dilation, time for the inhabitants of such a galaxy would slow down compared to the rest of the cosmos. If their stellar system were moving at a significant fraction of the speed of light, billions of years could pass for the outside universe while only a few thousand years pass for them. The motion of their galaxy through intergalactic space would also expose them to extreme cosmic radiation, which could require either advanced shielding technologies or biological adaptations to survive. If such a civilization were aware of their home galaxy's extreme velocity, they might attempt to influence its motion, either to slow it down or to direct it toward a particular region of the universe. If astronomers ever detect anomalous energy signatures or signals from a fast-moving galaxy, it could be evidence of an advanced civilization adapting to an extreme cosmic environment. Future telescopes such as the James Webb Space Telescope, the Vera Rubin Observatory, and new gravitational wave detectors will allow scientists to study ultra-fast galaxies in greater detail. Among the most anticipated discoveries is the detection of the first relativistic stellar system, one moving at over 50% of the speed of light, which would challenge our understanding of gravity and dark matter. Another breakthrough in a high velocity that unexpectedly changed, suggesting the unknown forces or even artificial manipulation. If one of these cosmic travelers vanished completely, it must observational evidence ways, or higher dimensional structures. Additionally, detecting a galactic hypercollision would reveal how energy transfers at the largest scales. The study of these extreme objects remains one of the most exciting frontiers in astrophysics. Whether they result from gravitational interactions, unknown cosmic forces, or even signs of intelligent engineering, such fast-moving galaxies push the boundaries of what we consider possible. As observational capabilities improve, we may soon uncover their true nature, possibly redefining our understanding of space, time, and the fate of the universe. If these high-speed galaxies exist in significant numbers, they may not be isolated anomalies but rather part of a greater cosmic pattern that has yet to be fully understood. Their existence challenges current astrophysical models, pushing the limits of our knowledge about gravity, cosmic expansion, and galactic evolution. They could also be linked to the formation of large-scale structures, revealing an unknown mechanism governing their motion at extreme velocities. One intriguing possibility is that these galaxies are not randomly propelled but instead follow gravitational highways formed by dark matter filaments. Some cosmologists propose that dark matter is distributed in a way that creates massive intergalactic superhighways, allowing certain stellar systems to move faster than expected. If this is true, these cosmic wanderers could provide crucial evidence about the large-scale structure and distribution of dark matter in the universe. Another theory suggests that fast-moving galaxies might be influenced by cosmic voids, vast empty regions with little to no matter. Instead of being pulled toward massive objects, these stellar formations could be repelled by these underdense regions, accelerating outward. Some scientists speculate that dark energy, the mysterious force driving the universe's expansion, might have local variations that push galaxies away rather than simply expanding space uniformly. If such galaxies are disproportionately found near cosmic voids, this could suggest that dark energy is more complex than previously thought. There is also the possibility that unknown fundamental forces accelerate these galaxies. While standard physics describes gravity as the dominant force at cosmic scales, alternative theories propose additional interactions affecting galaxies and clusters. If ultrafast galaxies accelerate in ways that cannot be explained by known gravitational effects, this could indicate the presence of a new fundamental force shaping the universe. Some researchers speculate that these stellar systems might be relics from an earlier phase of cosmic evolution. If physical laws or interactions between matter and dark matter differed in the early universe, certain galaxies may have been propelled to extreme velocities billions of years ago. This could mean that rather than being anomalies, these objects are remnants of a primordial event, offering insight into physics that no longer operates today. Another question is whether some of these galaxies might be artificial. If an advanced civilization had technology capable of manipulating gravitational fields, it could potentially control the motion of an entire galaxy. This could be done to escape a dangerous region of space, navigate toward a desired location, or even use galactic movement as a form of interstellar travel. If astronomers detect high-speed galaxies exhibiting controlled acceleration rather than purely natural motion, it could be a sign of large-scale engineering at work. Future observations will be crucial in determining whether these galaxies fit within known physical models or require new physics to explain their behavior. By analyzing their motion, astronomers may identify patterns revealing whether they travel randomly or as part of a larger cosmic structure. If they follow dark matter filaments, this could confirm the existence of gravitational highways shaping the universe. If they are concentrated near cosmic voids, this might indicate a previously unknown interaction between galaxies and dark energy. One of the most important breakthroughs could come from tracking the long-term trajectories of these cosmic speedsters. If their motion changes unexpectedly, defying known gravitational dynamics, it could suggest the presence of undiscovered forces. Additionally, if some of these galaxies appear to accelerate rather than simply maintaining constant speeds, this might indicate an unknown influence on their movement. Another groundbreaking discovery would be finding galaxies that appear to vanish. If a stellar system moves at extreme velocities and later disappears from observations, it might have crossed a cosmic boundary, such as the event horizon created by space expansion. This could provide direct evidence of galaxies escaping the observable universe, an idea long theorized but never confirmed. As observational technology advances, allowing astronomers to detect fainter, more distant objects, the study of ultra-fast galaxies will next-generation including the Square Kilometre Array and gravitational wave detector cover unknown galactic missions. These high-velocity be more complicated. It would suggest that the universe is far more dynamic than current models predict. Ultimately, these extreme galaxies could hold the key to solving some of cosmology's deepest mysteries. Whether they result from dark matter interactions, repulsion from voids, remnants of an ancient event, or even artificial constructs, their existence challenges fundamental astrophysical assumptions. Their study could not only redefine our understanding of galaxy evolution but also reshape our view of the universe itself. If these galaxies are more than just isolated anomalies, their movement could indicate that the universe's large-scale structure is far more active than previously thought. Their acceleration might be governed by unknown interactions between dark matter, dark energy, and intergalactic gravitational fields. If their motion cannot be fully explained by known mechanisms such as gravitational slingshots or black hole interactions, it could suggest that vast regions of space experience forces yet to be discovered. One of the most compelling possibilities is that these objects are responding to unknown gravitational waves or distortions in spacetime. If large-scale ripples in spacetime exist, perhaps caused by ancient cosmic events like the collision of supermassive black holes or remnants of a previous universe, they might subtly influence galaxy trajectories across billions of light-years. Future gravitational wave detectors could determine whether these galaxies are reacting to spacetime distortions beyond our current detection capabilities. Another intriguing question is whether these galaxies are linked to variations in dark energy. While dark energy is generally considered uniform, if high-speed galaxies tend to move toward or away from specific regions, it could mean that this force is unevenly distributed. Some parts of space might exert stronger repulsive forces, pushing entire galaxies to extreme velocities. If true, this would require a major revision of cosmological models, suggesting a far more complex expansion of the universe. It is also possible that these stellar formations reveal a new type of matter or interaction. If some galaxies accelerate in ways inconsistent with standard gravitational models, they might be affected by unknown particles or forces. For instance, if dark matter is not entirely passive but exhibits certain repulsive or dynamic properties under specific conditions, it might explain the unusual acceleration patterns observed. Alternatively, an undiscovered force acting at cosmic scales could first reveal its effects through these galaxies. A more radical idea is that these high-speed objects interact with hidden dimensions. Some string theory models propose that gravity may leak into additional spatial dimensions, causing unexpected deviations in galactic motion. If such galaxies are disproportionately found in certain regions of space, they might be interacting with higher dimensional structures, providing the first observational hint of extra dimensions. Another fascinating concept is whether ultrafast galaxies function as natural time machines. Due to relativistic effects, objects moving at extreme velocities experience significant time dilation, where time slows relative to the rest of the universe. If a galaxy were moving near the speed of light, an external observer might witness it aging much more slowly than surrounding cosmic structures. If civilizations exist within such galaxies, they could experience time on a vastly different scale, effectively becoming time travelers relative to the broader universe. The detection of these galaxies also raises fundamental questions about their long-term fate. If they continue accelerating, do they reach a threshold beyond which they can no longer interact with the rest of the universe? If so, does this imply the existence of cosmic escape routes, where matter can permanently exit the observable cosmos? If one of these stellar systems were to cross such a boundary, it might appear to slow and fade from view, eventually becoming undetectable. Observing such a disappearance would be among the most extraordinary discoveries in modern cosmology. Another consideration is whether ultrafast galaxies are indicators of an impending phase transition in the universe. If more of these stellar systems are found accelerating to extreme velocities over time, it could suggest a fundamental cosmic shift, possibly signaling a transition into a new state of physics. Some theoretical models propose that dark energy may eventually increase in strength, leading to the so-called Big Rip scenario, where galaxies, stars, and even atoms are torn apart as space expands at an accelerating rate. If these fast-moving galaxies are early signs of this process, they may be the first objects to reveal that the nature of the cosmos is evolving in ways we do not yet fully understand. As more advanced telescopes and computational models emerge, astronomers will be able to analyze high-velocity galaxies with unprecedented precision. If patterns emerge in their motion, they could reveal an underlying structure governing their trajectories. Some of these objects might also display unexpected compositions or energy signatures, suggesting interactions with forces beyond current understanding. Whether propelled by dark matter streams, gravitational distortions, or something even more exotic, these galaxies remain among the most enigmatic mysteries of the cosmos. The study of such extreme celestial objects has the potential to reshape our understanding of fundamental cosmic forces. Whether they are remnants of a previous cosmic cycle, indicators of hidden physics, or evidence of an undiscovered aspect of dark energy, their presence challenges the assumption that the universe is predictable and stable. Instead, they suggest a far more dynamic cosmos, where extreme motion and unknown interactions may one day redefine everything we know about space, time, and reality itself. If increasing numbers of fast-moving galaxies continue to be discovered, it could indicate that our understanding of the universe remains fundamentally incomplete. Their existence challenges traditional models of galaxy motion, hinting at unexpected forces at play or unknown interactions with cosmic structures. Future studies could determine whether these galaxies are simply anomalies or part of a larger, hidden pattern in cosmic evolution. One of the most crucial areas of research will be the long-term tracking of these cosmic travelers. If they exhibit variations in velocity or unexpected trajectory shifts, it could imply interactions with variable gravitational forces or invisible structures. Such deviations from expected motion would provide direct evidence of uncharted cosmic phenomena, potentially revealing undiscovered cosmic forces or gravitational anomalies. Advanced simulations and AI-driven analysis will be essential in mapping their paths and predicting their future movements. Another question is whether these galaxies interact differently with cosmic expansion. The accelerated expansion of the universe is attributed to dark energy, but hyperfast galaxies could provide new insights into how high-velocity objects behave within an expanding spacetime. If their movement deviates from standard cosmological expectations, it might suggest that space itself has hidden dynamics influencing their trajectories. Observing them over long time frames may offer clues as to whether space contains unknown factors that affect galaxies at extreme speeds. The role of dark matter in the motion of these high-speed stellar systems is another key question. If they exhibit velocities inconsistent with visible gravitational sources, it could suggest that dark matter plays a more active role in shaping their movement. Some theories propose that dark matter might not be entirely passive but could instead interact dynamically under specific conditions, forming invisible gravitational currents that direct galaxies along particular paths. If ultrafast galaxies are following these hidden flows, it would provide compelling evidence for the structure and behavior of dark matter on cosmic scales. There is also the possibility that these galaxies are linked to exotic astrophysical processes. Some hypotheses suggest the existence of previously unknown gravitational slingshot mechanisms capable of imparting immense velocity to entire stellar systems. If new classes of astrophysical events, such as interactions with rogue supermassive black holes or large-scale gravitational waves, are discovered, they could help explain why some galaxies achieve such extreme speeds. Investigating the environments around these objects could reveal whether they originate from regions of high gravitational instability. Another avenue of research is whether high-velocity galaxies represent a previously unknown evolutionary pathway for galactic systems. If some galaxies are ejected from dense clusters or experience prolonged high-speed motion through intergalactic space, they may undergo unique evolutionary processes. A galaxy moving at extreme velocity might lose its gas more rapidly, reducing its ability to form new stars. Over time, it could evolve into a dark, inactive system, devoid of significant star formation. If astronomers identify quiescent galaxies that appear to have once been high-speed objects, it could indicate that these stellar systems aged differently due to their extreme motion. Another intriguing possibility is that rapidly moving galaxies could serve as natural laboratories for testing relativistic physics on a galactic scale. Since objects moving at near-light speeds experience time dilation and other relativistic effects, their internal physics may subtly differ from stationary galaxies. If ultrafast galaxies exhibit unusual energy distributions or unexpected cosmic ray activity, they could provide an unprecedented real-world test of Einstein's theories at galactic scales. The potential for these galaxies to reveal hidden cosmic structures is another key area of study. If they consistently move toward or away from specific regions of space, it could suggest the presence of unseen mass concentrations, variations in dark energy, or even exotic gravitational anomalies. Some researchers speculate that hyperfast galaxies may act as natural probes of the universe's invisible framework, uncovering structures that otherwise remain undetectable. Large-scale surveys mapping their trajectories could provide new insights into the hidden architecture of spacetime. The ultimate fate of these galaxies remains uncertain. If one is moving at extreme speeds, does it eventually slow down due to cosmic interactions, or does it continue accelerating indefinitely? If some appear to gain velocity over time, it might indicate interactions with large-scale cosmic flows or even hidden dimensions. Conversely, if they eventually decelerate, it could suggest that intergalactic drag, dark matter interactions, or unknown gravitational effects gradually reduce their energy over billions of years. If any of these galaxies were observed to vanish from astronomical surveys, the implications would be profound. Such a discovery might suggest that certain galaxies are crossing into regions of space fundamentally different from our own, potentially supporting theories of cosmic gateways, wormholes, or even the multiverse. If a fast-traveling galaxy were to disappear without a trace, it would be among the most extraordinary astronomical findings in history, requiring a radical reconsideration of cosmic boundaries. As technology advances, the study of ultra-fast galaxies is likely to become one of the most significant fields in astrophysics. The ability to track them over millions or even billions of years could help resolve some of the biggest questions about the structure and evolution of the cosmos. Whether they reveal new forces, uncover exotic physics, or simply challenge our understanding of gravity on the largest scales, these extreme galaxies could hold the key to the next great discoveries in astrophysics. If these high-speed objects are part of a larger, hidden structure within the universe, their continued study may unveil aspects of the cosmos that remain undetected. They could be following unseen gravitational currents, responding to forces beyond our current understanding, or even moving toward a final destination beyond the limits of observable space. Their behavior might be signaling the presence of undiscovered cosmic phenomena, making them one of the most promising astrophysical mysteries of our time. One of the biggest questions surrounding ultra-fast galaxies is whether their trajectories are entirely random or if they exhibit patterns that suggest an underlying order. If their motion aligns with large-scale structures, such as cosmic filaments or dark matter streams, it would provide strong evidence that these stellar systems interact with an invisible framework shaping the movement of matter across billions of light-years. Future deep space surveys will be crucial in determining whether these galaxies follow specific paths or are simply the result of chaotic gravitational interactions. The possibility that hypervelocity galaxies are connected to large-scale cosmic expansion raises additional questions. If they are accelerating beyond expected limits, it could indicate that space itself does not expand uniformly. Some cosmologists propose that different regions of the universe may expand at varying rates due to fluctuations in dark energy density. If these high-speed galaxies are concentrated in areas of anomalous expansion, it might suggest that the acceleration of the universe is more complex than previously thought. Another potential factor influencing these fast-moving stellar systems could be unknown astrophysical events. While many are believed to have been ejected due to interactions with supermassive black holes or gravitational slingshots within dense clusters, there may be other unidentified mechanisms at play. If some galaxies reach extreme speeds without any apparent interactions, it could indicate the existence of new cosmic forces, undiscovered astrophysical explosions, or interactions with exotic forms of matter. A more radical hypothesis suggests that these galaxies might be revealing new physical laws that only become apparent on extremely large scales. In standard physics, galaxies should not be able to exceed certain velocity limits without external forces acting upon them. If some ultrafast galaxies are moving beyond these expected thresholds, it could suggest the presence of an unknown force or even a modification of general relativity that applies on the scale of galaxy clusters and beyond. If confirmed, this could revolutionize our understanding of gravity and possibly lead to a new theory that unifies relativity with quantum mechanics. Some physicists even speculate that hypervelocity galaxies might be linked to quantum effects on a cosmic scale. While quantum mechanics typically governs subatomic particles, some models suggest that quantum entanglement or other non-local effects might influence galactic motion under specific conditions. If high-speed galaxies exhibit unexpected correlations in their movement, it could be evidence that quantum processes play a role in shaping the structure of the universe at macroscopic levels. Another fundamental question is whether these cosmic wanderers represent a natural stage in galactic evolution or an extreme outlier. If they continue moving through intergalactic space, they may undergo drastically different fates compared to those remaining in galactic clusters. Over billions of years, such galaxies might lose their ability to form new stars as they deplete their gas supplies, ultimately evolving into dark, inactive systems drifting endlessly through the void. If astronomers identify evidence of such dead ultrafast galaxies, it could reveal entirely new processes governing the long-term fate of matter in the cosmos. The notion that hypervelocity galaxies might reveal the limits of the observable universe is another compelling possibility. If some move so fast that they eventually vanish from view, it might provide direct evidence that certain objects can reach cosmic horizons beyond which light can no longer return. If surveys show that these galaxies systematically fade from observations at certain distances, it could confirm that they are crossing into regions where spacetime itself becomes inaccessible. This would offer one of the strongest proofs that the universe has cosmic boundaries where information is permanently lost. Future discoveries might also include the first direct observation of a high-speed galaxy undergoing a major cosmic event, such as colliding with another galaxy or interacting with an unknown force. If a fast-moving system is observed to change direction unexpectedly, it could provide direct evidence of external influences shaping the universe at its largest scales. Detecting a hypervelocity galaxy accelerating in real time would be one of the most extraordinary findings in astrophysics, as it would suggest that an active mechanism is continuing to increase its speed. As technology advances, the study of these enigmatic galaxies will likely lead to some of the most profound discoveries in modern cosmology. Whether they are natural phenomena, remnants of a past cosmic event, or indicators of new physics, they challenge our current models of how the universe operates. Their motion may hold the key to unlocking secrets about dark matter, dark energy, cosmic expansion, and even the fundamental nature of space and time. Whatever the final explanation, these high-speed galaxies are among the most significant objects in the search for the deepest truths about the cosmos. If these hyperfast stellar systems continue to challenge existing astrophysical theories, their existence may force scientists to rethink fundamental aspects of cosmic evolution, gravity, and large-scale structure formation. These galaxies could provide insights into hidden cosmic mechanisms that remain undetectable through conventional means. Their study might ultimately lead to breakthroughs in understanding the true nature of dark matter, the effects of cosmic expansion, and the possible existence of previously unknown forms of energy or matter. One of the most significant research areas will be analyzing the environments from which high-velocity galaxies originate. If they are preferentially found in specific cosmic structures, such as dense galactic clusters, cosmic voids, or regions with unusually high dark matter density, it could reveal the conditions necessary for their formation. If these galaxies are disproportionately located in certain regions, it may indicate that large-scale gravitational flows, dark matter interactions, or even quantum effects play a role in their acceleration. Another crucial avenue of research involves the internal structure of ultrafast galaxies. If these objects move at extreme speeds through intergalactic space, their internal dynamics might differ significantly from those of stationary galaxies. For example, their gas clouds may be more compressed due to their rapid motion, potentially leading to unique star formation processes. Alternatively, they may lose their interstellar gas at an accelerated rate due to interactions with the intergalactic medium, causing an early shutdown of star formation. If hypervelocity galaxies display significantly different compositions or evolutionary paths, it could provide new insights into the long-term effects of high-speed motion on galactic evolution. A more speculative yet intriguing idea is that these fast-moving galaxies may be interacting with exotic forms of matter or energy that have yet to be identified. If some exhibit unexplained acceleration, it could suggest the presence of previously unknown interactions with dark matter or dark energy. Some theories propose that dark matter might not be entirely passive but, under rare conditions, could exert repulsive forces or interact with normal matter in unexpected ways. If these galaxies move in patterns inconsistent with known gravitational forces, they could provide the first observational evidence of such an interaction. Another question is whether their extreme motion affects their gravitational influence on surrounding space. General relativity predicts that massive objects moving at high velocities can distort spacetime, potentially generating gravitational waves. If ultrafast galaxies are massive enough and moving fast enough, they might produce detectable gravitational disturbances. Future gravitational wave observatories could potentially detect these signals, offering a new way to study these objects and their interactions with the universe. The idea that hypervelocity galaxies might be linked to new aspects of cosmic expansion is another emerging area of interest. While dark energy is considered responsible for accelerating the universe's expansion, its properties remain mysterious. If fast-traveling galaxies move in ways that correlate with variations in cosmic expansion, it could indicate that dark energy is not uniform but instead varies across space and time. This would suggest a more dynamic, evolving universe than previously believed. There is also speculation that some ultrafast galaxies might be influenced by interactions with undetected ultramassive black holes. If a galaxy were to pass close to an extraordinarily massive black hole, far beyond those currently observed, it could experience an extreme gravitational slingshot effect, reaching velocities much greater than expected. Discovering such an event would challenge assumptions about black hole mass limits and their role in shaping galactic motion. Ultimately, the study of hypervelocity galaxies may uncover fundamental truths about the universe's large-scale structure, unknown cosmic forces, and the hidden nature of spacetime itself. As research continues, these extraordinary objects may reveal that the cosmos is far more dynamic and complex than we ever imagined. Another unexplored possibility is whether ultrafast galaxies are linked to large-scale cosmic turbulence. Some cosmologists proposed that the universe contains vast, swirling flows of matter, driven by gravitational interactions across billions of light-years. If such turbulent motions exist, these high-velocity stellar systems might be following these currents, much like how oceanic flows shape the movement of ships on Earth. Confirming the existence of such large-scale gravitational streams could offer new insights into the dynamics of galaxy motion and reveal that the universe is far more fluid and dynamic than previously assumed. A truly radical hypothesis is that hypervelocity galaxies are related to hidden cosmic gateways or wormholes. If space contains natural shortcuts through higher dimensions, certain galaxies might be ejected at extreme velocities upon interacting with these structures. While wormholes remain theoretical, some models predict that such objects could generate gravitational anomalies capable of launching stellar systems into intergalactic space at extraordinary speeds. If some high-speed galaxies exhibit characteristics suggesting an origin from an unknown source, it could provide indirect evidence for the existence of these enigmatic structures. The long-term fate of these fast-moving celestial objects remains an unresolved question. If they continue moving at extreme velocities, do they eventually leave the observable universe? Could they be traveling toward a region of space with fundamentally different physical properties? If some hyperfast galaxies disappear from future observations, it might suggest that they are entering a domain where the laws of physics behave differently, offering potential clues about cosmic boundaries. Conversely, if these galaxies eventually slow down, it could indicate the presence of an unknown cosmic drag force, possibly related to interactions with dark matter or intergalactic plasma. Future telescopic missions, such as the Next Generation Extremely Large Telescope (ELT), and upcoming space observatories, will be crucial in studying these galaxies at unprecedented levels of detail. These advanced instruments will allow astronomers to examine their light signatures, gravitational influences, and motion patterns with far greater precision. If some high-velocity stellar systems display unexpected energy distributions, relativistic time dilation effects, or unexplained spectral shifts, it could provide direct evidence of new physics. Another avenue of research will involve determining whether some ultra-fast galaxies show signs of artificial manipulation. If an advanced civilization possessed the ability to influence the motion of an entire galaxy, it might leave detectable signatures, such as precise, unnatural acceleration patterns. If these objects are observed changing course in ways that defy natural gravitational interactions, it could indicate an engineered cosmic event on an unimaginable scale. Additionally, if any of these galaxies emit anomalous energy outputs or unusual radiation signatures, it might suggest the presence of technological influences beyond our current understanding. As research into these mysterious galaxies progresses, their study could have implications beyond astrophysics. If they reveal new properties of gravity, dark matter, or cosmic expansion, it could reshape our understanding of the universe's structure and evolution. If some high-speed galaxies exhibit characteristics suggesting hidden dimensions, unknown forces, or artificial control, they could represent the first observable evidence of phenomena challenging modern physics. Whatever the ultimate explanation, these extreme galaxies remain a profound mystery that may hold the key to some of the deepest secrets of the cosmos. If these hyperfast stellar systems continue to be a focal point of astrophysical research, their study may ultimately lead to groundbreaking discoveries about the very fabric of reality. Their extreme motion challenges conventional astrophysical theories and raises profound questions about cosmic evolution, the true nature of spacetime, and the existence of unknown forces. The deeper astronomers investigate, the more they may uncover about the unseen structures governing the universe. One of the most urgent priorities for future research is mapping the precise distribution of these galaxies throughout the cosmos. If they cluster in specific regions or align with large-scale cosmic filaments, it could suggest that they are being influenced by a hidden gravitational framework. If, however, their distribution appears random, it might indicate that their acceleration results from individual astrophysical events rather than large-scale cosmic forces. Resolving this question could determine whether these galaxies are the product of known gravitational interactions or if they point to an unexplored mechanism shaping the universe. Another critical area of research will involve analyzing the spectra of high-velocity galaxies to determine whether they exhibit unexpected energy distributions or relativistic distortions. If some are traveling at significant fractions of the speed of light, they should experience measurable time dilation effects, where internal processes, such as star formation and supernova explosions, occur at different rates compared to normal galaxies. Observing these relativistic distortions would provide one of the most direct tests of Einstein's theories on galactic scales, refining our understanding of how extreme motion influences cosmic structures. One of the more speculative but intriguing ideas is that ultrafast galaxies might not be randomly ejected, but instead moving toward a destination. If these galaxies appear to accelerate toward a common region, it could suggest that they are being drawn toward an unknown attractor. Some cosmologists propose that massive, undiscovered concentrations of dark matter or even hidden spacetime structures may be exerting influence. If hypervelocity galaxies follow similar trajectories, it could provide evidence for unseen mass concentrations or new physics governing large-scale galactic motion. Another possibility is that these galaxies might serve as natural tests for modified gravity theories. Some physicists propose that gravity behaves differently at extreme distances or under high-velocity conditions, leading to alternative models such as MOND, modified Newtonian dynamics, or emergent gravity. If ultrafast galaxies deviate from expected motion based on standard general relativity, it could indicate that gravity itself requires modification, potentially leading to a new understanding of fundamental physics. If hyperfast galaxies continue to challenge standard cosmology, their study may lead to a fundamental rethinking of how galaxies move and interact on the largest scales. Their motion could provide indirect clues about the nature of dark energy, the role of dark matter, and even whether hidden dimensions influence cosmic structure formation. The continued search for these enigmatic objects could ultimately reshape astrophysics, revealing that the universe is far more complex, dynamic, and interconnected than we currently perceive. The potential role of dark energy in accelerating ultrafast galaxies remains an area of active exploration. While dark energy is generally thought to act uniformly across the cosmos, some theories propose that it may exhibit localized variations, creating hot spots where the expansion of space is stronger. If these high-velocity stellar systems tend to originate from or move toward regions with dark energy fluctuations, it could suggest that dark energy is not merely a passive background force but instead plays a dynamic role in galactic motion. Another unexplored avenue is whether hypervelocity galaxies are remnants of a past cosmic event, such as a large-scale gravitational disturbance that occurred billions of years ago. Some models suggest that during the early universe, interactions between quantum fields and cosmic inflation could have created regions of extreme motion, ejecting galaxies at high speeds. If these fast-moving galaxies are disproportionately found at certain redshifts corresponding to specific cosmic epochs, it might indicate that their motion was influenced by primordial energy conditions rather than recent gravitational interactions. One of the most radical hypotheses is that these rapidly moving celestial objects result from interactions with hidden dimensions of spacetime. Some string theory models propose that our universe is embedded in higher dimensional space, and under certain conditions, gravitational interactions with these extra dimensions could impart unexpected accelerations to massive objects like galaxies. If ultrafast stellar systems exhibit motion that cannot be explained by known physics, it could be the first observational evidence that extra dimensions have measurable effects on the universe. Another speculative yet increasingly discussed idea is whether some high-speed galaxies might have been artificially manipulated. If an advanced civilization had the ability to control gravitational forces on a galactic scale, it might be able to move its home galaxy or even entire star systems to escape a cosmic catastrophe, avoid hostile forces, or facilitate intergalactic travel. While this remains speculative, the discovery of a fast-traveling galaxy with unexpected energy outputs, unusual structural patterns, or signs of controlled acceleration would be one of the most extraordinary findings in astronomy. A crucial test for understanding these mysterious objects will be whether any are observed actively accelerating in real time. If a galaxy is detected with a measurable increase in velocity over observational periods, it would suggest that an unknown force or mechanism is continually acting upon it. Observing such an effect would be unprecedented, providing direct evidence of forces beyond conventional gravity shaping large-scale cosmic structures. As observational techniques improve, astronomers will also attempt to determine whether hypervelocity galaxies evolve differently compared to other galaxies. If they experience higher rates of stellar evolution, black hole activity, or cosmic ray emissions, it could suggest that extreme motion influences their internal processes. If these fast-traveling galaxies appear systematically younger or older than expected based on their environments, it might indicate that high-speed motion alters the long-term evolution of galaxies in unexpected ways. One of the biggest open questions remains whether ultra-fast galaxies are a rare phenomenon or if they are far more common than currently believed. If future deep-field surveys reveal large numbers of these objects, it might indicate that our current models of galaxy motion need revision. If, however, they remain rare outliers, it could suggest that their formation requires highly specific conditions that occur only in exceptional circumstances. If any hypervelocity stellar systems disappear from future observations, it could provide the strongest evidence yet that the universe contains boundaries or hidden structures that certain objects can cross. If a fast-moving galaxy were to vanish completely, leaving no detectable remnants, it might support theories suggesting that hyperspeed objects can enter regions of space that operate under fundamentally different physics. Detecting such an event would require long-term monitoring and precise measurements of galactic motion over decades or even centuries. Future space missions, including next-generation gravitational wave detectors, advanced infrared telescopes, and AI-driven sky surveys, will play a critical role in deepening our understanding of these enigmatic celestial objects. If these technologies reveal new and unexpected properties about hypervelocity galaxies, it could revolutionize our knowledge of cosmic motion, spacetime, and the hidden forces shaping the universe. Ultimately, these mysterious high-speed objects may hold the key to answering some of the deepest questions about the cosmos. Whether driven by dark matter flows, influenced by cosmic expansion, or propelled by unknown physics, their motion challenges everything we know about the fundamental laws governing the universe. The next discoveries in this field may not only transform our understanding of galaxy dynamics but could also provide insights into the ultimate fate of the universe itself. If ultrafast galaxies continue to reveal unexpected properties, their study may offer the first observational evidence for entirely new cosmic phenomena. These galaxies, moving at extreme velocities through the vastness of intergalactic space, could be the key to unlocking secrets about dark matter, dark energy, the fabric of spacetime, and the fundamental limits of physics. As research progresses, astronomers must develop more precise observational techniques, advanced computational models, and new theoretical frameworks to fully comprehend what drives their motion and what their existence implies for the nature of the universe. One of the most critical areas of future research will be determining whether hypervelocity galaxies exhibit anomalies in their gravitational interactions. If these galaxies move in ways that defy conventional gravitational dynamics, it could indicate the presence of additional gravitational forces that only act at extreme velocities. Some physicists have proposed that gravity may behave differently on cosmic scales than it does within galaxies, suggesting that ultrafast stellar systems could provide an experimental test for alternative gravity models, such as emergent gravity or theories involving extra dimensions. If some high-speed galaxies experience gravitational shifts or unexplained accelerations, it could suggest that they are interacting with forces beyond our current understanding. These findings could ultimately reshape modern astrophysics, revealing hidden aspects of gravity, the role of dark matter, and even the existence of unknown cosmic forces guiding the motion of galaxies at the largest scales. Another possibility is that ultrafast galaxies are interacting with cosmic structures that remain invisible to conventional observation. The existence of dark matter streams, gravitational corridors, or cosmic superhighways has been theorized, but direct evidence remains elusive. If these high-velocity stellar systems follow precise paths that align with unseen gravitational frameworks, it could indicate that they are being influenced by vast networks of gravitational fields shaped by dark matter. This would provide some of the strongest evidence yet that dark matter is not merely a passive background component of the universe but an active force shaping the motion of galaxies across intergalactic distances. The nature of dark energy and its role in accelerating hypervelocity galaxies remains an open question. If dark energy is not a uniform force but instead fluctuates across space, it could create regions where galaxies experience additional acceleration. If these fast-traveling galaxies are concentrated in zones of heightened dark energy activity or near pronounced spacetime distortions, it might indicate that dark energy is dynamic rather than constant. Such a discovery would represent a major shift in our understanding of cosmic expansion, suggesting that the universe's accelerated growth is far more complex than previously assumed. A major challenge in studying these mysterious objects is determining whether they are truly moving at extreme velocities relative to the rest of the cosmos or if their apparent motion is influenced by unknown distortions in spacetime. Some theoretical models propose that spacetime itself may contain warps or folds, allowing galaxies to appear to move at high speeds while actually following curved paths through the universe. If ultrafast stellar systems are found to be bending around unseen gravitational distortions, it could provide evidence that space itself is structured in ways that challenge classical relativity. Another possibility is that hypervelocity galaxies serve as indicators of large-scale cosmic phase transitions. Some theories suggest that the universe undergoes slow but fundamental shifts in its physical properties over time. If these high-speed galaxies are accelerating due to changes in the underlying fabric of spacetime, they might be early signs that the universe is entering a new evolutionary phase. Certain models proposed that the universe could eventually transition into a different physical state, altering the fundamental constants of physics. If ultrafast stellar systems are responding to such a shift, it could be a precursor to a major cosmic event. There is also speculation that these fast-moving celestial objects may result from interactions with exotic astrophysical structures, such as primordial black holes, ultramassive dark matter clusters, or even cosmic strings, hypothetical spacetime defects that could exert extreme gravitational forces. If high-speed galaxies are observed moving away from certain regions at extraordinary velocities, it might indicate that they have been affected by the gravitational pull of an unseen cosmic entity. Discovering the source of such interactions could lead to the identification of entirely new classes of astrophysical objects. The long-term fate of these ultra-fast galaxies remains one of the greatest mysteries in astrophysics. If they continue accelerating indefinitely, do they eventually leave the observable universe? If so, what happens to them beyond the cosmic event horizon? If some hypervelocity stellar systems are crossing into regions where physical laws function differently, it could suggest that the universe has boundaries, hidden dimensions, or even transition zones that separate distinct cosmic regions. If any of these fast-moving galaxies disappear entirely, it might serve as evidence that they have entered a realm where information cannot return to us. Future space-based observatories will be essential for tracking these high-speed objects over long periods to determine whether they are following predictable trajectories or if their motion is influenced by unknown cosmic forces. AI-driven sky surveys could detect patterns in their motion that might hint at large-scale cosmic structures or interactions with invisible mass concentrations. If unexpected acceleration trends are observed, it could suggest that these galactic travelers are experiencing forces that defy conventional models of cosmic motion. One of the most speculative but intriguing possibilities is that hypervelocity galaxies might have been influenced by intelligent intervention. While this idea remains far outside mainstream astrophysics, some theorists have suggested that a sufficiently advanced civilization could manipulate gravitational forces on a galactic scale. If some ultrafast stellar systems show signs of unnatural motion, precise acceleration, or patterns inconsistent with natural astrophysical processes, it might indicate an engineered event. Detecting anomalous energy emissions or unexplained course adjustments in high-speed galaxies would be among the most profound discoveries in the history of science. Another crucial test will be whether these fast-moving galaxies experience significant internal changes due to their motion. If traveling at extreme velocities through intergalactic space affects their ability to form new stars, retain interstellar gas, or sustain long-term stability, it could suggest that hypervelocity motion actively reshapes galactic evolution. If certain high-speed stellar systems are found to be devoid of young stars or have unusually disrupted structures, it might indicate that their motion is altering them over time. If these ultra-fast galaxies continue to be discovered in greater numbers, it could indicate that they are not rare anomalies but rather a fundamental component of cosmic evolution. If their numbers are found to be increasing over time, it might suggest that the conditions leading to their formation are becoming more common as the universe evolves. If they remain relatively rare, it could mean that they are the result of exceptional circumstances, making them valuable cosmic laboratories for studying extreme physics. Ultimately, these high-speed objects represent one of the most fascinating frontiers in astrophysics. Their existence challenges long-standing assumptions about cosmic motion, gravity, and the large-scale forces shaping the universe. Whether they are natural outliers, the result of unknown interactions, or indicators of new physics, they hold the potential to redefine our understanding of the cosmos. The next major discoveries in this field may provide insights not only into how galaxies move but also into the deeper mysteries of space, time, and the fundamental nature of reality itself. If these ultrafast stellar systems continue to defy conventional astrophysical models, their study may reveal deeper truths about the forces governing the cosmos. These galaxies, moving at extraordinary velocities, may be signaling the presence of unknown interactions that have remained undetected. Their extreme motion could be linked to dark matter flows, gravitational anomalies, hidden dimensions, or even cosmic phase transitions that reshape the universe over vast timescales. One of the most important questions surrounding these high-velocity objects is whether they are accelerating due to a singular event, such as an interaction with a supermassive black hole, or if their motion is being continuously influenced by an external force. If their speeds remain constant or gradually decrease due to interactions with intergalactic plasma, it would suggest that they are remnants of past gravitational interactions. However, if some hypervelocity galaxies are found to be gaining speed, it could indicate that an unknown force is still acting upon them, requiring entirely new physics to explain their continued acceleration. If future gravitational wave observatories detect disturbances linked to these galaxies, it could provide a new method for studying the interplay between high-speed motion and the curvature of spacetime, bringing us closer to understanding the true nature of the cosmic web and the hidden forces shaping the universe. The relationship between ultrafast galaxies and dark energy remains an area of growing interest. If dark energy is responsible for the acceleration of the universe's expansion, could it also be exerting a localized influence on the motion of individual stellar systems? Some models suggest that dark energy may not be a uniform force but could fluctuate, creating zones of increased acceleration. If hypervelocity galaxies are found in specific regions where dark energy appears stronger, it might indicate that the expansion of the universe is not as smooth and uniform as previously believed. Another possibility is that these high-speed galaxies represent an entirely new category of astrophysical objects, stellar systems evolving under extreme conditions, potentially giving rise to unexpected physical effects. If these galaxies experience rapid gas loss as they travel through intergalactic space, they may undergo unique evolutionary processes, leading to the formation of exotic stellar populations or large-scale structural distortions. If ultrafast galaxies differ significantly in composition or star formation rates from normal galaxies, it could indicate that extreme motion alters galactic evolution in ways we have yet to fully explore. Some cosmologists propose that hypervelocity stellar systems could be part of a larger cosmic cycle. If the universe undergoes periodic transformations, with regions of space experiencing gravitational shifts over time, then these fast-moving galaxies might be the first observable evidence of a large-scale cosmic phase transition. If high-speed galaxies are preferentially found at certain cosmic distances, corresponding to different eras in the universe's history, it could suggest that their motion is linked to changes in the fundamental structure of spacetime itself. There is also the possibility that these extreme stellar systems provide indirect evidence of quantum effects at cosmological scales. While quantum mechanics is typically confined to the microscopic world, some theories suggest that quantum fluctuations could influence large-scale cosmic structures. If ultrafast galaxies exhibit statistical correlations in their motion that defy classical explanations, it could indicate that quantum entanglement or other quantum effects play a role in shaping galactic trajectories on the largest scales. One of the biggest unanswered questions is whether these hypervelocity galaxies are isolated anomalies or part of a broader trend. If future deep field surveys reveal that more galaxies are reaching extreme velocities, it might indicate that the universe is experiencing a shift in its large-scale gravitational balance. If, on the other hand, these objects remain rare outliers, it could suggest that their formation depends on specific, extreme conditions, making them valuable test cases for studying high-energy cosmic interactions. Another area of ongoing research is whether these fast-traveling galaxies might be crossing into regions of the universe where physics behaves differently. If some galaxies move toward zones where their light becomes increasingly redshifted and eventually vanishes, it could be a sign that they are approaching cosmic boundaries beyond which information cannot return. If a hypervelocity stellar system were to disappear completely, it would be one of the strongest pieces of evidence yet that the universe contains regions where space, time, or fundamental laws undergo profound transformations. One of the most speculative yet intriguing possibilities is that these high-speed galaxies may have been influenced by intelligent intervention. While this remains highly theoretical, if a civilization were capable of controlling gravity on a galactic scale, it might possess the ability to move entire star systems or even entire galaxies. If some ultrafast stellar systems exhibit unnatural patterns of motion, precise velocity shifts, or energy outputs that do not match known astrophysical processes, it might suggest deliberate acceleration. While such a discovery would be extraordinary, it would also redefine our understanding of advanced technological possibilities in the cosmos. Ultimately, the study of these mysterious high-speed galaxies represents one of the most exciting and unexplored frontiers in modern astrophysics. Whether they are relics of past cosmic events, indicators of new physics, or evidence of unknown cosmic forces, they challenge the very foundations of our understanding of the universe. The next generation of telescopes, AI-driven sky surveys, and advanced gravitational wave detectors may provide the first definitive answers about these enigmatic objects. If these ultrafast galaxies are natural phenomena, their study could refine our knowledge of galactic motion, dark matter interactions, and cosmic expansion. If they are driven by unknown physics, they could lead to entirely new theories that reshape how we understand gravity, space, and time. And if, in the most extreme scenario, they are found to be influenced by intelligent manipulation, it would mark one of the greatest discoveries in the history of science. As research into these high-speed stellar systems continues, the potential for groundbreaking discoveries remains vast. Whether they hold the key to the secrets of dark matter, quantum gravity, or hidden cosmic architectures, they are among the most fascinating and mysterious objects in the observable universe. The answers they provide may not only change our understanding of galaxies but could also redefine the nature of reality itself. These hypervelocity stellar systems remain one of the most enigmatic mysteries of the cosmos, challenging our understanding of gravity, dark matter, and the fundamental forces shaping the universe. Whether they are remnants of past cosmic events, indicators of unknown physics, or signs of vast, hidden structures, their motion defies conventional explanations. As future telescopes and AI-driven surveys continue to track their trajectories, they may reveal profound insights into spacetime, cosmic expansion, and the ultimate fate of the universe. Whatever the final answer may be, the study of ultrafast galaxies has the potential to reshape our perception of reality itself. Creating a text of 100,000 characters requires significant effort. It'll provide you with a long, detailed, and engaging text about the Whirlpool Galaxy, packed with scientific details and research, aiming to captivate the audience. Let me start, and feel free to guide me if you'd like adjustments. The Whirlpool Galaxy, catalogued as Messier 51, M51, and often referred to as NGC 5194, stands as one of the most iconic and visually stunning examples of a spiral galaxy in the observable universe. Nestled within the relatively small constellation Canes Venatici, this celestial masterpiece has long been a subject of fascination for both amateur stargazers and professional astronomers. It represents a quintessential example of a grand design spiral galaxy, with its sharply defined arms and luminous core serving as a beacon for those studying galactic evolution and interactions. Located approximately 31 million light-years away from Earth, the Whirlpool Galaxy is relatively close in cosmic terms, making it a prime target for telescopic observations. Its visual magnitude of 8.4 renders it visible through small telescopes, while its intricate details can be fully appreciated with more advanced equipment. The galaxy spans roughly 76,000 light-years across, making it slightly smaller than the Milky Way, yet its beauty and complexity are no less impressive. One of the most intriguing aspects of the Whirlpool Galaxy is its interaction with its smaller companion, NGC 5195. This satellite galaxy, which is physically connected to M51 via a luminous bridge of stars and gas, has profoundly influenced the Whirlpool structure. The gravitational forces between these two galaxies have induced significant tidal effects, resulting in the formation of the Whirlpool's distinctive, well-defined spiral arms. These arms are not merely visual features, they are regions of intense star formation, often referred to as stellar nurseries. Massive clouds of hydrogen gas within these arms collapse under gravity to form new stars, some of which are among the brightest and most short-lived in the universe. The Whirlpool Galaxy has been extensively studied in multiple wavelengths of light, from radio to X-rays, revealing a wealth of information about its composition, dynamics, and history. Observations in the ultraviolet and optical spectra highlight the regions of active star formation, where young, hot stars illuminate surrounding gas clouds. Infrared studies, such as those conducted by the Spitzer Space Telescope, have provided insights into the distribution of cooler interstellar dust, which serves as the raw material for future generations of stars. Meanwhile, X-ray observations, particularly those made by the Chandra X-ray Observatory, have identified numerous high-energy phenomena within the galaxy, including black holes, neutron stars, and supernova remnants. The central region of the Whirlpool Galaxy is of particular interest to astronomers. Like most large galaxies, M51 hosts a supermassive black hole at its core. This black hole, with a mass estimated to be millions of times that of the Sun, exerts a profound influence on its surroundings. Material falling into the black hole forms an accretion disk, where gravitational and frictional forces heat the gas to extreme temperatures, causing it to emit radiation across the electromagnetic spectrum. These emissions make the galactic nucleus a bright source of X-rays and radio waves, offering a glimpse into the otherwise hidden processes occurring near the event horizon. The interaction between M51 and NGC 5195 has not only shaped the Whirlpool's spiral arms but also triggered waves of starburst activity. As the smaller galaxy passes through the disk of M51, it compresses the gas and dust within the spiral arms, leading to the rapid formation of stars. This process is thought to be responsible for the unusually high rate of star formation observed in the Whirlpool Galaxy. Such interactions are a common feature in the life cycles of galaxies and are believed to play a crucial role in their evolution. The Whirlpool Galaxy has also been a fertile hunting ground for supernovae, with several notable events recorded in recent decades. These stellar explosions, marking the violent deaths of massive stars, are not only spectacular to observe but also serve as laboratories for studying the physical processes governing the universe. Supernovae eject vast amounts of heavy elements into the interstellar medium, enriching future generations of stars and planets. They also produce neutrinos, elusive subatomic particles that provide insights into the fundamental forces of nature. One of the most remarkable aspects of studying the Whirlpool Galaxy is the ability to observe the processes of galactic interaction and evolution in real time. The gravitational dance between M51 and NGC 5195 is a dynamic process that unfolds over millions of years, offering astronomers a unique opportunity to study the stages of galactic collisions and mergers. These interactions are not merely chaotic, they are also creative, giving rise to new structures and triggering bursts of star formation that breathe new life into the galaxies involved. Technological advancements in telescopes and observational techniques have played a key role in deepening our understanding of the Whirlpool Galaxy. Instruments such as the Hubble Space Telescope have provided high-resolution images that reveal the intricate details of its spiral arms and star-forming regions. Ground-based observatories equipped with adaptive optics systems have also made significant contributions, enabling astronomers to overcome the blurring effects of Earth's atmosphere. Furthermore, radio telescopes have mapped the distribution of neutral hydrogen gas within M51, shedding light on the galaxy's large-scale structure and dynamics. The study of the Whirlpool Galaxy extends beyond its immediate vicinity. As a nearby example of a grand design spiral galaxy, M51 serves as a benchmark for understanding similar systems throughout the universe. Its well-defined features make it an ideal target for testing theories of galactic structure and dynamics, while its ongoing interaction with NGC 5195 provides valuable insights into the role of mergers and tidal forces in shaping galaxies. Researchers have also used the Whirlpool Galaxy as a testing ground for advanced computational models of galaxy formation and evolution. By simulating the gravitational interactions between M51 and its companion, scientists can reproduce the observed structures and gain a deeper understanding of the physical processes involved. These models not only enhance our knowledge of the Whirlpool Galaxy but also improve our ability to interpret observations of more distant and less well-resolved systems. The Whirlpool Galaxy has inspired countless scientific discoveries and remains a source of wonder and curiosity. Its striking appearance, with its luminous core, sweeping arms, and dynamic interactions, captures the imagination of all who observe it. Whether through the lens of a telescope or the pages of a scientific paper, M51 invites us to ponder the intricate and interconnected nature of the cosmos. As technology continues to advance, the Whirlpool Galaxy will undoubtedly yield even more secrets, enriching our understanding of the universe and our place within it. This majestic cosmic structure, often referred to as the spiral wonder of Cain's Venatici, captivates observers not only with its aesthetic brilliance but also with the wealth of scientific knowledge it holds. The celestial pair of the Grand Vortex Galaxy and its smaller companion, the stellar bridge neighbor, NGC 5195, represents a dynamic system where the forces of gravity orchestrate a cosmic ballet. This dance between the two entities serves as a living example of how galactic collisions shape and redefine the universe on massive scales. The galactic whirlpool system, as it is sometimes called, has been pivotal in advancing our understanding of starburst phenomena. The regions within its prominent spiral arms, saturated with hydrogen alpha emissions, highlight zones where stellar nurseries thrive. Here, vast molecular clouds collapse under gravitational forces, birthing stars that are not only young, The intense ultraviolet radiation from these newborn stars ionizes the surrounding gas, causing it to glow and illuminate the spiral structure. Studies of this phenomenon have provided astronomers with invaluable data on the interplay between star formation and galactic evolution. The cosmic dynamo of M51 has also been a laboratory for exploring the effects of galactic interaction. When the satellite galaxy, the irregular companion, NGC 5195, grazes the disk of the primary galaxy, it creates shock waves that ripple through the interstellar medium. These waves compress gas, inducing bursts of star formation while also leaving behind arcs of older stellar populations. Observations of these effects have confirmed theoretical predictions about the role of tidal forces in triggering star formation. In the heart of the interstellar whirlpool, the core region reveals a supermassive black hole cloaked in an accretion disk of superheated matter. The behavior of this black hole has been scrutinized using X-ray and radio telescopes, revealing its episodic bursts of high-energy radiation. These emissions, sometimes accompanied by relativistic jets, provide critical data for studying the behavior of matter under extreme gravitational conditions. By comparing the activity of this galactic nucleus with others across the universe, researchers refine models of black hole growth and galaxy central dynamics. The gravitational interaction of the starlight whirlpool system with its companion also plays a crucial role in redistributing angular momentum within the larger galaxy. This redistribution explains the tightly wound nature of its spiral arms, which differ from the looser structures seen in other spiral galaxies. Through detailed kinematic studies using spectroscopic data, astronomers have mapped the velocity patterns of stars and gas within the system, confirming the presence of density waves that sustain the spiral arm's distinct shape over time. The galactic tidal beauty, with its richly detailed arms, has been a source of inspiration for the study of dark matter. The rotational velocities of stars in the outer regions of the galaxy suggest the presence of a dark matter halo that extends well beyond the visible boundaries. This hidden mass exerts a gravitational influence that stabilizes the galaxy and maintains the integrity of its spiral arms. Observations of the whirlpool-like entity have significantly contributed to the broader understanding of how dark matter shapes galaxies across the cosmos. From the vivid colors of the grand spiral nexus, observed in optical and ultraviolet wavelengths, to the infrared glow of its dusty interstellar medium, every observation provides a piece of the cosmic puzzle. Astronomers have leveraged instruments such as the Hubble Space Telescope and the Very Large Array to capture high-resolution images and spectra of this galactic system. These datasets not only enhance our understanding of this particular galaxy but also serve as a comparative baseline for studying more distant systems that share similar characteristics. The stellar collision nexus remains a site of frequent supernova activity. These cataclysmic events, often occurring in the spiral arms, are observable as brief yet extraordinarily bright flashes. Each supernova provides a unique opportunity to study nucleosynthesis, the creation of heavy elements such as gold and uranium. By analyzing the light curves and spectral lines of these events, scientists unravel the complex processes that govern the life cycles of massive stars and their explosive deaths. The cosmic turbine of NGC 5194 exemplifies how interactions between galaxies fuel dynamic processes. The bridge of material linking the primary galaxy to its companion is a testament to the power of gravitational forces. This bridge, composed of stars, gas, and dust, allows for material exchange between the two galaxies, further complicating and enriching their evolution. Simulations of this interaction, conducted using advanced computational models, have allowed scientists to recreate the observed structures and dynamics, shedding light on similar processes occurring in other galactic systems. As our understanding of the intergalactic vortex deepens, it becomes increasingly clear that this galaxy is more than just a striking visual feature in the night sky. It is a cornerstone for scientific exploration, offering insights into a wide array of cosmic phenomena, from the formation of planetary systems to the large-scale structure of the universe. With each new discovery, the whirlpool system continues to remind us of the intricate and awe-inspiring nature of the cosmos. The celestial whirlpool pair, with its iconic sweeping arms and brilliant central hub, continues to unravel the mysteries of the universe. While its beauty has captivated stargazers for centuries, it is the depth of scientific data embedded in its structure that makes it invaluable to astrophysics. The primary galaxy, often described as the spiral dynamo of the north sky, acts as a natural laboratory for studying the forces that shape galaxies, drive star formation, and govern cosmic interactions. One of the key areas of research in this galactic wonder is the role of density waves in forming and maintaining its spiral arms. Unlike solid structures, these arms are composed of stars, gas, and dust moving in and out of gravitational traffic jams as they orbit the galactic center. These density waves compress gas clouds as they pass through, triggering waves of star formation. This self-sustaining process ensures that the whirlpool maintains its elegant spiral structure over millions of years. The ability to study this phenomenon so clearly in this system has helped astronomers understand how other grand design galaxies form and evolve. The intergalactic dance of NGC 5194 and its companion, NGC 5195, also reveals the long-term consequences of galactic mergers. Observational data shows that the smaller galaxy has already passed through the disk of the larger one multiple times, leaving behind tidal tails, arcs, and plumes of stars and gas. These remnants of gravitational interaction act as a memory of the encounter, offering a timeline of past collisions. Such detailed records are rare and provide critical evidence for understanding how galaxies like the Milky Way may have formed through similar interactions in the past. The heart of the cosmic vortex, the nucleus of NGC 5194, is not merely a quiet gathering of old stars. Instead, it is a bustling hub of activity dominated by the supermassive black hole at its center. With masses millions of times that of the Sun, this black hole exerts immense gravitational pull, drawing in surrounding gas and dust. As material spirals inward, it heats up to millions of degrees, releasing high-energy radiation that can be detected across vast cosmic distances. This phenomenon makes the nucleus of the whirlpool an active galactic nucleus, AGN, albeit less luminous than quasars. By studying AGNs like this one, scientists gain a better understanding of the relationship between black holes and their host galaxies. The Stellar Bridge Galaxy is also a treasure trove for studying the life cycle of stars. Its spiral arms host a variety of stellar populations, from bright blue giants in their infancy to red giants nearing the end of their lives. Using spectroscopy, astronomers can determine the chemical composition of these stars and their surrounding gas. This data reveals how generations of stars have enriched the galaxy with heavier elements, a process known as chemical evolution. These elements, forged in the cores of stars and released during supernovae, are the building blocks of planets, life, and even ourselves. Moreover, the whirlpool's proximity and clarity make it an ideal target for studying the interplay between magnetic fields and star formation. The magnetic field lines, mapped using radio telescopes, align with the spiral arms, guiding the movement of charged particles and influencing the collapse of gas clouds into stars. Understanding these magnetic processes is crucial for piecing together the puzzle of star formation in galaxies across the universe. In recent years, the galactic gravitational showpiece has also become a focus for research into dark matter. The rotation curve of NGC 5194, which plots the orbital velocity of stars and gas at varying distances from the center, does not behave as expected based solely on visible matter. Instead, it suggests the presence of an unseen halo of dark matter that provides additional gravitational pull. This dark matter halo not only stabilizes the spiral structure but also plays a vital role in shaping the galaxy's overall dynamics. The whirlpool-like nexus has even contributed to the study of cosmic expansion. Using the Cepheid variable stars within its arms, astronomers have refined measurements of the Hubble constant, a key parameter that describes the rate at which the universe is expanding. By comparing these observations with those of other galaxies, researchers can test models of cosmology and explore mysteries such as dark energy. Beyond its scientific contributions, the cosmic tidal sculpture continues to inspire awe and wonder. Its breathtaking images, captured by observatories like Hubble, have been widely shared and studied, igniting public interest in astronomy and space exploration. Each image reveals new layers of complexity, from the intricate dust lanes that weave through its spiral arms to the faint tidal streams that hint at its tumultuous past. As telescopes become more advanced, the Whirlpool Galaxy and its companion will undoubtedly yield even more secrets. The upcoming generation of observatories, such as the James Webb Space Telescope, promises to peer deeper into the infrared, unveiling hidden star-forming regions and the faintest structures in the system. These discoveries will not only enhance our understanding of the Whirlpool Galaxy but also provide broader insights into the processes that govern the evolution of galaxies throughout the cosmos. The Whirlpool system, with its interplay of beauty, science, and cosmic history, stands as a symbol of humanity's quest to understand the universe. Each observation, whether of its spiral arms, its active nucleus, or its gravitational interactions, brings us closer to answering the fundamental questions about our origins and the nature of the cosmos itself. Should I continue delving into more aspects or refine specific sections further? The majestic spiral of Cain's Venatici remains a cornerstone in the study of galactic morphology, providing astronomers with unparalleled insights into the forces and processes that shape galaxies. Its ability to reveal complex structures, dynamic interactions, and a range of stellar phenomena has made it a focal point for both theoretical and observational research. The whirlpool, or stellar maelstrom, as it is sometimes called, serves as a gateway to understanding the broader mechanisms that govern cosmic evolution. One of the most striking aspects of the interstellar dynamo is the intricate balance between chaos and order. Despite the violent gravitational interactions with its companion, the spiral nexus has maintained its well-defined structure. This paradox is explained through the concept of density wave theory, where spiral arms are not static features but rather regions of higher density that move through the galaxy. This dynamic behavior allows the arms to persist even as individual stars and gas clouds move through them. The study of this mechanism has implications far beyond M51, helping astronomers decode the behavior of spiral galaxies across the universe. The galactic tidal duo offers a rare glimpse into the early stages of a galactic merger, a process that can take billions of years to complete. Simulations show that the smaller galaxy, often referred to as the stellar intruder, is gradually losing its distinct identity as it becomes engulfed by the larger whirlpool. This ongoing interaction provides a live demonstration of how galaxies grow and evolve through accretion and mergers, processes that are thought to have played a major role in the formation of massive elliptical galaxies observed today. Another remarkable feature of the celestial whirlpool pair is the bridge of material connecting NGC 5194 and its companion. This stellar and gaseous bridge is a direct result of tidal forces, where the gravitational pull of the smaller galaxy distorts the disk of the larger one. The material within this bridge includes young stars, molecular gas, and interstellar dust, all of which are subjected to intense radiation and gravitational shearing. Detailed observations of this bridge have provided critical data on how tidal interactions redistribute material within and between galaxies, fueling star formation and triggering bursts of activity. The whirlpool, often referred to as the cosmic engine, also stands out as a prolific factory for stellar creation. Infrared observations reveal the presence of dense molecular clouds within its spiral arms, where conditions are ripe for the birth of new stars. These regions, often hidden in optical wavelengths by interstellar dust, are illuminated in the infrared spectrum, offering a clearer picture of the early stages of stellar formation. The ongoing starburst activity in the whirlpool is not just a localized phenomenon but a cosmic relay, as the energy and materials produced by these stars will shape the galaxy's future. The stellar whirlpool system is also a key site for studying the end stages of stellar evolution. The supernovae observed in its arms are not isolated events but rather the natural culmination of a star's life cycle. When a massive star exhausts its nuclear fuel, it undergoes a catastrophic collapse, releasing a tremendous amount of energy and ejecting heavy elements into the surrounding medium. Each supernova observed in M51 has provided unique data on the mechanisms of core collapse, the properties of neutron stars and black holes, and the enrichment of the interstellar medium. Beyond the stars, the whirlpool galaxy reveals the enigmatic role of dark matter in shaping cosmic structures. While the visible mass of the galaxy accounts for its luminous features, it cannot explain the observed rotational velocities of stars in its outer regions. This discrepancy points to the presence of a vast halo of dark matter, an invisible but critical component of the galaxy. By studying the rotational dynamics of M51, astronomers have refined models of dark matter distribution and its influence on galactic evolution. The galactic vortex of NGC 5194 also contributes to our understanding of feedback mechanisms in galaxies. The central black hole, through its accretion activity, generates powerful winds and jets that can influence star formation across the galaxy. This feedback loop, where the energy output of the nucleus regulates the availability of gas for star formation, is a key factor in determining the life cycle of galaxies. Observations of these processes in M51 have helped validate theories about the coevolution of supermassive black holes and their host galaxies. The whirlpool's companion, sometimes dubbed the stellar companion nexus, plays an equally vital role in shaping the primary galaxy. As it orbits and interacts with NGC 5194, it acts as both a disruptor and a catalyst. The gravitational forces exerted by the smaller galaxy create tidal streams and induce bursts of star formation, while also redistributing angular momentum within the system. This dynamic interplay offers a microcosm of the larger processes at work in galaxy clusters, where interactions between member galaxies drive the evolution of the entire system. On the observational front, the whirlpool-like entity has been a proving ground for cutting-edge technology. Instruments like the Atacama Large Millimeter/Submillimeter Array, ALMA, have been used to study the cold molecular gas in the galaxy, providing a detailed map of the raw materials available for star formation. Meanwhile, the James Webb Space Telescope promises to unveil even more details about the galaxy's hidden regions, shedding light on its youngest stars and the earliest phases of stellar evolution. The celestial tidal marvel continues to captivate astronomers and the public alike. Its visual appeal, combined with its scientific significance, makes it a cornerstone of modern astrophysics. As our tools and techniques for exploring the cosmos improve, the Whirlpool Galaxy will undoubtedly remain a focal point for discovery, offering new insights into the nature of the universe and our place within it. The spiral marvel of Cain's Venatici, often hailed as a galactic masterpiece, remains an enduring focus of cosmic exploration. Its prominent features an ongoing process